Welcome back. In this presentation, I actually want to show you how we can use the antiderivative to figure out the area under a curve. And hopefully, actually, I'm going to focus more a little bit on the intuition. So let's actually use an example from physics. I'll use distance and velocity. And actually, this could be a good review for derivatives or actually an application of derivatives. So let's say that I describe the position of something moving. Let's say it's S. Let's say that S is equal to, I don't know, 16 t squared, right? So S is distance. Let me write this in the corner. I don't know why the convention is to use S as the variable for distance. One would think, well, actually I know. Why won't they use D? Because D is a letter used for differential, I guess. So S is equal to distance. And then T is equal to time. So this is just a formula that tells us the position, kind of how far has something gone after X many, let's say, seconds, right? So after like 4 seconds, we would have gone, let's say the distance is in feet and this is in seconds. After 4 seconds, we would have gone 256 feet. That's all that says. And let me graph that as well. Graph it. Okay, that was a horrible line. Let me actually use the line tool. Might have better luck. It's slightly better. Actually, let me undo that too, because I just want to do it for positive t, right? Because you can't really go back in time. For the purposes of this lecture, you can't go back in time. So, well, that'll have to do. Okay. So the curve. This curve will essentially just be a parabola, right? It'll look something like this. Right? So actually, if you look at it, I mean, you could just eyeball it, that the object, every second you go, it's going a little bit further, right? So it's actually accelerating. And so what if we wanted to figure out what the velocity of this object, right? This is, let's see, this is d, this is t, right? And this is, I don't know if it's clear, but this is kind of 1/2 of a parabola. So this is the distance function. So what would the velocity be? Well, the velocity is just, what's velocity? It's distance divided by time, right? And since this velocity is always changing, we want to figure out the instantaneous velocity. And that's actually one of the initial uses of what made a derivative so useful. So we want to find the change, the instantaneous change with respect to time of this formula, right? Because this is the distance formula. So if we know the instant rate of change of distance with respect to time, we'll know the velocity, right? So ds dt is equal to, so what's the derivative here? It's 32t, right? And this is the velocity. Maybe I should switch back to, well, let me write that. V equals velocity. I don't know why I switched colors, but I'll stick with the yellow. So let's graph this function. This will actually be a fairly straightforward graph to draw. Oh, that's pretty straight. And then let me draw the x-axis. Well, I'm doing pretty good. Okay. And so this, I'll draw it in red. It's just going to be a line, right? 32t, it's a line with slope 32. So it's actually a pretty steep line. I won't draw it that steep because I'm going to use this for an illustration. So this is the velocity. Now so this is velocity. This is that graph, and then this is distance, right? So in case you hadn't learned already, and maybe I'll do a whole presentation on kind of using calculus for physics and using derivatives for physics, but if you have the distance formula, its derivative is just velocity. And I guess if you view it the other way, if you had the velocity, its antiderivative is distance, although you won't know where at what position the object started. In this case, the object started at position of 0, but it could be at any constant, right? You could have started here and then curved up. But anyway, let's just assume we start at 0. So the derivative of distance is velocity. The antiderivative of velocity is distance. Keep that in mind. Well, let's look at this. Let's assume that we were only given this this graph, and we said, this is the graph of the velocity of some object. And we want to figure out what the distance is after t seconds, right? So this is the t-axis, and this is the velocity axis, right? So let's say we were only given this, and let's say we didn't know that the antiderivative of the velocity function is the distance function. How would we figure out what the distance would be at any given time? Well, let's think about it. If we have a constant, this red is kind of bloody. Let me switch to something more pleasant. If we have over any small period of time, right, or if we have a constant velocity, when you have a constant velocity, distance is just velocity times time, right? So let's say we had a very small time fragment here, right? I'll draw it big, but let's say this time fragment is really small. And let's call this very small time fragment, let's call this delta t, or dt, actually. The way I view of dt is it's like a change in time that's unbelievably small, right? So it's like almost instantaneous, but not quite. Or you can actually view it as instantaneous. So this is how much time goes by. You can kind of view this as a very small change in time. So if we have a very small change of time, and over that very small change in time, we have a roughly constant velocity. Let's say the roughly constant velocity is this. Right? This is the velocity. So we have, over this very small change in time, we have this roughly constant velocity that's on this graph. Actually, let me do it here. We have this roughly constant velocity. So the distance that the object travels over the small time would be the small time times the velocity, right? It would be whatever the value of this red line is times the width of this distance, right? So what's another way? Visually, I kind of did it ahead of time, but what's happening here? If I take this change in time, right, which is kind of the base of this rectangle, and I multiply it times the velocity, which is really just the height of this rectangle, what have I figured out? Well, I figured out the area of this rectangle, right? Right? The velocity at this moment times the change in time at this moment is nothing but the area of this very skinny rectangle. Skinny and tall, right? It's almost infinitely skinny, but we're assuming for these purposes it has some very notional amount of width. So there we figured out the area of this column, right? Well, if we wanted to figure out the distance that you travel after, let's say, I don't know, let's say t sub naught, right? This is just a particular t. After t sub naught seconds, right? Well, then all we would have to do is we would just do a bunch of dt's, right? You'd do another one here, and you'd figure out the height of the area of this column. You'd figure out the area of this column, the area of this column, right? Because each of the areas of each of these columns represents the distance that the object travels over that dt, right? So if you wanted to know how far you traveled after t sub 0 seconds, you would essentially get, or an approximation would be the sum of all of these areas. And as you got more and more, as you made the dt's smaller and smaller, skinnier and skinnier, skinnier, and you had more and more and more and more of these rectangles, then your approximation will get pretty close to, two things. It'll get pretty close to, as you can imagine, the area under this curve, or in this case, a line. But it would also get you pretty much the exact amount of distance you've traveled after t sub naught seconds. So I think I'm running into the 10-minute the wall. So I'm just going to pause here, and then I'm just going to continue this in the next presentation.